For other videos or problems like this for Intro to Stat Methods for Business, you can go to SYX Studies, link is in the description box below. Given some data, how can we come up with an equation or a model to predict future Y values? In this case, we want to come up with an equation that when we plug in a certain amount of candy, we can predict our revenues. Now, I know the candy is in decimals, but bear with me. Just imagine that you can cut up a Kit Kat or any chocolate into 5.9 pieces. So to give you an idea of what we're looking for, I'm going to go and select the data, and I'm going to click Insert and go here to the first scatter plot. I'm going to right click on the data points, add trend line, go over here, make it, orange, dash type the first line, and this is what I'm talking about. All we're trying to do is just find an equation for this orange line. Why do we want to do that? Because this is what we call the line of best fit. It is the line that best fits our data points. Our blue data points, those are our real Y values, our real revenues. And we're just trying to find a line that best fits those data points, and it fits it so well that I could use it to predict future data points, future Y values. And so how do we get that equation? We go to data and we go to data analysis. If you don't have this, just search up options, go to add-ins, go to go, and then make sure that this first one, analysis toolpath, is checked, click OK, and then you'll be able to see data analysis. So when you click that, go and click regression and then click OK. For your Y range, just highlight your Y values, including your label. Same thing with the X, check labels because you included your labels. Output range is where you want the summary output to be outputted. I'm just going to click on this cell, and then I'm going to click on residuals and residual plots, and I'll explain that in a second. Just click OK. And then we have this stuff over here. I'm just going to move it over here. Now, all we need to come up with the equation of the orange line is right here. So that line, we call it Y hat because it's going to give us our Y value, but not our real Y value, just a predicted Y value. And so that hat on the Y stands for predicted, estimated Y value. And the way that I remember the equation is baby, but instead of the A, it's just going to be bow, and then we're going to say B, and then separate that by a plus sign, and then times X. And so in the summary output, it's in order. The intercept is our bow, and B is just the slope of this column candy X over here. So in other words, this is equal to our bow, which is our intercept, which is this, plus our B, which is the slope of this column candy over here. So that's just going to be that times the actual variable. And this is the equation for this orange line over here. That's it. So we can use this to predict future Y values. So let's say I want to predict what my revenues, what my Y value is going to be when I give out 6 pieces of candy. So then my Y hat, my predicted value when X is 6 is just going to be this plus our slope times amount of candy, which is 6, and that is your answer. So my predicted revenues, my Y hat, is going to be this over here. Now to interpret this, for one piece of candy, my revenues are going to increase by $2.07. And then to interpret this, if I give out 0 candies, so 0 times this just cancels out, and we're just left with this. So if I give out 0 candies, then my revenue is negative $3 because there's a negative there. And that makes sense. If I make that X 0, I'm literally just left with my Y-intercept. So that's interpreting. Now we know that this is the line of best fit, but how much really does it fit the data? Like how good really is this line? Well, we can look at a little bit of some statistics to figure that out. So one is the R-squared. Another one is the p-value. So in essence, you want a high R-squared and a low p-value, lower than 0.05 to be specific. So R-squared just represents the proportion of the variance or the difference in your Y values that can be explained by your model. And so the more that can be explained, the better your model is. That's why a higher R-squared, the better this model is. Now, we want a low p-value, lower than 0.05. And if you're not good with visual math, you can't see that there's, an E 6 decimal places to the left, and you can simply do a nice little function. If our p-value is less than 0.05, then tell me that it's significant. If not, tell me that it's not significant. If it's significant and you have a higher score, then that's a really good indication that your model is a really good one to predict future Y values. Some other indications would be the residual plot, which is why I told you to check residuals. So you should also see this residual plot. And what we look for in a residual plot is randomness. We don't want to see any pattern because that means that we failed to capture something in our model. Our residuals should be random, which it is. And so that's another indication that this is a good model. It's a good equation to predict future Y values. We also have some assumptions, things that we assume when we use these models. First, we assume that it's linear, and that's easy to prove. You could just look at the scatter plot, see that it's linear. It's not quadratic. You don't see any parabola patterns here. Second, that it's normal. This means means that our data is normally distributed. For that, you can look at histograms or box plots. So if you select the data, you can go to insert and maybe look at a box plot. It's a little bit skewed, but for the purposes of this video, let's pretend it's normal. Finally, we assume that we have equal variance. That means that our residual plot does not look like this. If your residual plot looks like this, then that means that your model is violating the equal variance assumption, because equal variance just means the difference between the points. So as the x values increase, you'll see it goes small, small, and then bigger, bigger. So the differences, the variances between the residuals, the blue points, are not equal. They're different as x increases, and so therefore it violates the equal variance assumption. But our residual plot does not look like that, so we are good. And finally, our values have to be independent of each other, meaning that the residual plots don't look like this. This is mostly, when you deal with time series data that's been collected over a series of time where some data values might be dependent on other data values. If they are, we say that those data values are autocorrelated, meaning they are correlated to other previous data values. And when we plot the residual plots, they sometimes have a cyclical effect, an up and down movement, and then that would be a violation of the independence assumption. But luckily for us, again, we have a really nice random residual plot. So all of these together, looking at the R squared, high R squared, low p-value, less than 0.05, having all of these assumptions, it all points that this is a really fair model to use to predict future Y values. Some other things that I want to talk about, something called SSR, SSE, and SST. SSR stands for regression sum of squares, and it simply just represents the amount of variance that can be explained by the relationship between x and y. And then SSE is the opposite. It's the amount of variance that can't be explained, and then SST is just the sum of these two. So if we look at the sum of SSR plus SSE, we're going to get 78.76, which is the same thing as SST. Another thing that you want to know is if you take SSR over SST, remember that SST is the total amount of variation, the difference in the y values. So if you take the total amount of variation that can be explained over the total amount of variation that there is, then that gives you R squared, which is the proportion of the variation in y that can be explained by the relationship between x and y, aka the model, the equation. And so SSR over SST is your R squared. And these also come with their own degrees of freedom over here, but to be specific, our degrees of freedom over here for SST is n-1. N is just our observations, okay? This is just how many values we have. We have 14, that's what n is. So 14 minus 1, that's 13. SSE, the degrees of freedom, is equal to n minus k minus 1. When you're doing linear regression, k is always 1, because k just represents how many x variables you have, or how many slopes you have, same thing. Or in other words, how many independent variables you have, however you want to take it. And because in linear regression, we only deal with one variable, then k is equal to 1. But when we get to multiple linear regression, we might have a second x variable, and then that means we would have a second slope. So then that means our k is 2, because we have two x variables, or two slopes, however you want to think about it. So with linear regression, k is always equal to 1. So in this case, n, which is 14, minus k, which is 1, that's already 13, minus 1 again, that's 12. And then SSR, the degrees of freedom, is equal to just k. And again, k is equal to 1 because we only have one x variable. Now the last and final thing I wanted to mention is we have something called the standard error of the estimate. This just measures the variability of the real y values from the predicted y values. In other words, it measures the difference between the blue dots and any dots on our orange line. So real values and any predicted values. And that is this number right here. And we denote that by SYX. And unlike R squared, which is a proportion, the standard error is an actual number, and this is a small number. And if we look at the graph, we can see why it's small, because the blue dots, the real y values, and the predicted y values of the dots on the orange line are very close together. So the difference between them is small, so the standard error is small. That means that our model, our equation for the orange line, is a good line to predict future y values, because that line is really close to actual real values. So our answers, our estimates, are going to be more accurate than if we had a standard error that was bigger. If it was bigger, that means that our blue dots would be farther away from the predicted, orange line, and then that means that our orange line wouldn't be good to predict future y values because it's not even close to the blue dots, the real y values. And sometimes they'll give you a summary output and they'll just kind of like blank out some of the things, and sometimes it's going to be this and you're going to have to find what it is given other stuff. And the formula for SYX, if they don't give it to you, you can calculate it yourself. itself is going to be equal to the square root of SSE divided by n minus 2. So if you take the square root of SSE, which is this, and divide that by n, which is this, minus 2, we will get the same answer over here. I believe I've covered everything, and I'll see you in the next video.